It was like 7 or 8 people. But anyway, this is a 2-part series. This is kind of like a dual thing because whether you're going to the Coast Guard, Navy, Marine Corps, Coast Guard, you're going to be in Naval Aviation, and if you're going Air Force, you're going to be going through an initial flight screening, and everything is going to merge into the T6 aircraft.
All right.
And also what I'm going to do is I'm going to send you a POH as well. And you can just kick around with that and read that. But basically, there's 5 major topics that we're going to cover. The 5 major topics are aerodynamics, navigation, weather, regulations, and engine propulsion systems. Okay. And so
down into the 6 weeks, that is API.
Yeah.
That's not okay.
And if you don't have a private pilot certificate, you are going to be required to take an FAA written.
Okay.
So yeah, that's something. That's another thing. But kind of all of this is kind of it kind of encompasses a major portion of the FAA written, but there's a lot of information absorbed in the FAA written, and so I recommend just digging in it as soon as possible.
Isn't there something small before API 2? It's called like initial flight screening or something like that, IFS?
That's for the United States Air Force.
Okay.
API kind of does that a little bit. It's kind of like a similar thing. But I'll have more information as we go along here.
Okay.
As we zero in on things. Okay, so the first thing that we're going to talk about is you're going to have enabling objectives.
ELOs.
Yeah.
Yeah, we had those at OCS.
Cool. So you're going to have enabling objectives, and these are going to be major things that you are going to have to kind of know, like the back of your hand. And that's primarily what we hit on. Now, in this first lesson, a lot of this is going to be a lot of definitions. And primarily in aerodynamics, there's going to be a lot of what am I trying to say? There's going to be a lot of definitions, so this is going to be kind of boring, I guess, a little bit. But the first enabling objective is you're going to have to be able to define what a scalar is. And as I go along here, and this is going to be recorded, so you can come back, even if you don't get it all, you can come back and you can look at the video. Now, every video will not be recorded because, this is pretty much for marketing, and when I get the final course put together, know the timelines and all that and everything. So scalar is the first thing that we are going to have to be familiar with. A scalar is, it relates to a quantity, having only magnitude, not direction. Now you find this in physics. Let's see. Velocity is a scalar because I could be going 5 meters per second northwest or northeast or north-south or whatever. I could be driving northbound on I-95 at 55 miles an hour northbound. Okay, so that's the difference between speed and velocity. Velocity has a direction assigned to it, whereas speed was just boom. I'm going 55 miles an hour. So a scalar has magnitude. It does not have direction. The next thing, I think we all know what a vector is, correct?
No. Well, I'm sure if you brief me on it.
A vector basically is showing or demonstrating direction and magnitude. All right. It's a quantity that represents direction and magnitude, like lift. Like when we did our 4 forces of flight, when we would talk about that in your astb-e prep, we showed you arrows. And so you saw a vector going up, you saw a vector going forward, 1, 2. Okay, that's all a vector is.
All right, got it.
And it's just basically, it's to represent displacement. It can be used to represent velocity, acceleration, or force, like the 4 forces of flight, like lift, weight, thrust, drag. So it's just labels. All right. So let's see here. You're not going to let me highlight, are you? Okay, that's fine. This is the instructor version. Okay. The next definition that we're going to cover, and like I said, this is going to be all definitions, but definitely stuff that you will need to know. All right. Displacement. Okay, it's the distance and direction of a body's movement. Okay, and the example I have posted on the message board is an airplane flies east at 100 nautical flies east 100 nautical miles. Okay, so in this, a body has moved somewhere. Okay, you got up, you moved from your bedroom to the kitchen, or kitchen to the bathroom. All right, so something is being displaced. All right, we clear there?
Got it.
All right. Next thing is velocity. And we talked about velocity a little bit, the difference between speed and velocity. Calculating it is the same way. All right. It will be distance divided by time. But the difference between speed equals distance over time, velocity equals distance over time. The difference is velocity will actually have a direction. And we also have in the notes here, we also have an example, an airplane flies south at 400 knots. All right, speed is a scalar. Okay, so you could be moving at 55 miles an hour, but we don't necessarily have to assign a direction to it. All right, acceleration. And while we're here talking about acceleration, we will talk about the formula for acceleration. You will need that. All right. So acceleration is the rate and direction of a body's change of velocity. All right. Acceleration is acting on us right now at 9.8 meters per second squared. So as far as the formula goes for acceleration, acceleration is equal to what we call V sub 1 minus V sub 0 over T, and time in seconds. So a good way to be able to kind of quantify that is, let's say you're on 95, you're getting onto an on-ramp, okay? So you're going about 30 miles an hour, and you're going to accelerate to 50 miles an hour. Let's say this roadway, county road you're getting onto is 50 miles an hour is the limit, and it takes you 10 seconds to accelerate to that speed of 50. So V sub 1 is going to be 50 minus 30, because that is your initial speed that you start in miles per hour. And we'll say that it takes 10 seconds. So all we would need to do is subtract 30 from 50, and that will give us 20, right? And then 20 over 10 would be a numerical value of 2. But the way we say this is the acceleration is 2 miles per hour per second. All right. And you have to understand, just like gravity, can you see the board okay? Are the colors looking?
Yes.
Okay.
Yep.
So 2 miles per hour per second, that's how we talk about acceleration, which means in that 10 seconds from 30 miles an hour to 50 miles an hour, every second that passed, there was a pile-on. Okay, there was a pile-on, which means the first second I went from 30 to 32, the second, 34, 36, 38, and so on and so on.
That's understandable. I get it.
All right, force. All right.
And is this message board going to be accessible after the call-ins?
No, it is.
Oh.
It is not. It is, but it is being recorded.
Okay.
So you can go back. You can go back
Right.
and look at the video and stuff. And
Also, one thing you could do is you could copy the message board into like a Word document or something.
okay. And then it'll be like a transcript almost then, right?
Right, exactly.
Okay, all right. I can see what I can do about that. I won't close.
Like for the definitions, you know?
Okay. All right, so force. It's a push or pull exerted on a body. For instance, a aircraft power plant could be producing 1,000 pounds of thrust, pushing a jet through the sky. So that's what force is. All right. Now, a lot of times in navigation, when we work with vectors, which are basically the arrows that have a magnitude and direction. All right, let me scroll down in my notes. Okay. Basically, it's kind of like, we could look at it like the Cartesian coordinate plane. We have a y and an x-axis. All right, and 1, 2, 3, 1, 2, 3. All right, so we have a force exerting itself in this direction, and we have a force exerting itself in this direction. All right, so we could label this force A and this force B, but the resultant direction is just basically where we're going to end up. That is the resultant. So the resultant is a component of the vertical and the horizontal, and so this is basically where all the forces are going to concentrate themselves on. Now, when would you see something like this? In API, you would see something like this when they talk about turning. And remember this, what turns an airplane? The horizontal component of lift. The horizontal component of lift. And I'll put that in the notes too. Learn how to spell, Kieno. Oh, no. All right. That uppercase H is there, but no worries. Okay. Some other definitions that we're going to have to talk about, and we'll go deeper into the horizontal component of lift, but we just need to know that there are forces acting on a body, and this resultant force is going to be the net after we put in or plug in all these forces. All right. Mass. Mass is the quantity of molecular material that comprises an object. Okay. So if we look at what has more mass, a marshmallow or a brick, the brick has more molecular material. So the brick has more mass than the marshmallow. Now, you can have more mass and you could actually have less weight. It just depends on the material and the density of it. All right. All right. Volume is the amount of space occupied by an object. All right. And density is mass per unit volume. All right. And I'm going to give us some examples here. All right. Now, density equals mass over volume. So that's a formula that we're going to have to keep in mind. Density equals mass over volume. Force equals mass times acceleration. Okay, so our mass is going to be in kilograms most of the times. Our acceleration, meters per second squared normally. force is going to be in newtons. All right. So density is mass over volume. Force equals mass times acceleration. And the force will be in newtons. The mass will be in kilograms. And meters per second squared.
And acceleration is miles per hour per second.
Yes, if we're thinking about U.S. customary units and not standard international units.
Okay.
No, system international, SI units. Okay. And system international, it will be meters per second squared. In the U.S. customary, it could be miles per hours per second. It could be feet per second squared. But what you're going to do is you're going to have units that you're going to start out with, and you're just going to stick to those units when they give them to you in the form of a question. Okay. You got all that?
Yes.
Okay. Work equals force times displacement. And it will be W equals F, the force. Some people say FD. Some people use an S to measure displacement. But as long as you know that this is force and this is displacement, you'll be okay, whether they use a D or an S. I've seen some professors say, okay, well, I use S. And other ones be like, I use D. So
what would S stand for?
It's a displacement. But I think this is more practical. Displacement.
Yeah.
I know, right? But I've just seen it different ways. And I've asked professors, like, why do you use the S? And he's like, oh, well, that's the way I was taught it. You know, when I was in school, my professor taught it that way.
No good reason is the answer.
So yeah, there's no, all right. The next formula that we need to look into is energy. Okay. And energy, we have to look at it as total energy. So total energy is equal to kinetic energy plus potential energy. Okay. Total energy will be measured in joules. All right, so this will be measured in joules. And this breaks down into a formula. And this potential energy breaks down into a formula. All right. Potential energy, mass times gravity times height. And then kinetic energy is 1/2 mv squared. All right. So mass times gravity, gravitational pull, which is 9.8 meters per second. The mass will be in kilograms with system international units, SI units. And the height will be in meters normally. 1/2 mv squared for kinetic energy. Mass times velocity, how fast is it moving in meters per second. So we have to understand that kinetic energy is energy of motion. Potential energy is kind of stored energy. Let me give you an example. Let's say we're on a roller coaster, and the roller coaster goes up and then it comes down. Okay. Now, total energy is never going to change. Total energy is never going to change. So either our roller coaster, and Jake, don't laugh at my artwork.
No, it's not.
So total energy is always going to be the same, okay? Because energy cannot be lost or it can't be destroyed. It's just there, and it's either going to be, it's going to be like a seesaw, like our class 1 lever. Either the energy is going to be tilting this way or the energy is going to be tilted this way. Now, the energy in motion is kinetic energy. But now, while we are building, we have to have energy. We have to have a motor or chains or something pulling this roller coaster up to the top. Okay? After that, if you've ever ridden on a roller coaster, what's it do? It right, it takes you up, 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 up. When it gets to the top, then you got that little pause. Okay. At this point, the energy is stored in potential energy.
It's all potential energy at that point.
And then, poof, then boom, and then we're going down. Okay. So it's just important to remember the formulas. Potential energy is mass times gravity times height, and then kinetic energy is 1/2 mv squared, which is mass and velocity squared. Now, I know we've covered the 3 laws of motion. The first law is called the law of equilibrium, or the first law, Newton's first law of motion. It's the law of equilibrium. And what that states is a body at rest tends to remain at rest, and a body in motion tends to remain in motion. Okay? Which means your airplane, it's parked. Okay? It's going to pretty much sit still unless some outside force acts on it, be it a tow vehicle or you actually bump the throttle and get it moving. Okay? Once you get it moving, it's going to tend to remain in motion until we apply brakes, reverse throttle, or maybe we're taxiing uphill and friction applies. Okay? So that's the first law. All right. The law of equilibrium. All right. Now, if we're going to talk about the law of equilibrium, could you give me a definition for equilibrium? What in your mind is equilibrium?
In terms of, so.
Yeah, what does it mean? And if you know.
Equilibrium means that an object is, to me, is equally balanced. There's no outside forces that are acting on it. And
it could be because we have equilibrium in flight, which is a concept that is an enabling objective that you would have to explain. Because another or FAA test question that I've seen for years, over 20 years, when are all the forces in equilibrium in an airplane? And it's when an airplane is in constant unaccelerated flight. Okay, we're flying at, I don't know, 200-300 knots. We're not going to 301, 302, 303, and we're not slowing down to 299, 298, 297. Follow me? We're just at a constant speed. So thrust is equal to drag at that point, and lift is equal to weight. So make no mistake, there are forces at work here, all right? But they're just in balance, okay? It's kind of like, let me give you another example of equilibrium. When someone bails out, when somebody, our airborne rangers, when they go to jump school, okay, 9.8 meters per second squared exists to a certain point. Okay, all right, I got it back. Okay, so when you have like airborne rangers, when they do halo jumps, a halo jump is a situation where they actually have to jump out of plane with oxygen masks on. All right, because they're very high altitudes and atmospheric pressure is low at a high altitude, and so they're going to need supplemental oxygen when they bail out. So what happens is 9.8 meters per second squared is acting on their bodies. So like I said, when we think about acceleration, because that's acceleration, the gravitational pull, my little stick man, okay, and he's bailing out. So we have gravity, 9.8 meters per second squared is acting on that soldier that bailed out. Okay, let's put his little backpack on. Anyways, okay, so after 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, what is this? Okay, we jump out the plane. What is the soldier's speed after 2 seconds?
9.8 meters a second.
Okay, well, hold on now. Because after the first second, we have 9.8. And this is why I told you got to remember the pylon. After 2 seconds, he or she is actually 19.6. Yeah, 19.6. At 3 seconds, we add another 9.8. That's what we call acceleration. It ain't slowing down, it's speeding up. Okay? So
as soon as he jumps, it's 9.8 meters per second, but after that, it's like if you were looking at a chart, it would be a straight linear, like 45-degree angle.
Yeah, definitely. It's just a pylon. So after 1 second, 9.8, 15.6. After 10 seconds, this guy's already moving at 98 meters per second.
When does he reach equilibrium?
The person reaches equilibrium at terminal velocity. Okay. It's when he or she, or the jumper, is going to reach the equilibrium point. Now, what's causing the equilibrium?
When the person's drag would equal, what's the other force that's coming? Weight?
No, brother. You ever been driving when you were a kid? Stick your hand out the window?
Yes.
What's fighting your hand? Air molecules. Okay? So as he or she jumps, gravitational acceleration is being caused, but at the same time, the opposite force acting against that person is the proverbial hand stuck out the window type thing. And so the air molecules are like, whoa, slow down. Now what happens is the air molecules produce enough force to stop the acceleration. The person's still falling, but the acceleration has stopped.
Right.
You follow me? So that is the point of equilibrium.
So terminal velocity is when equilibrium is reached and acceleration is stopped. Is that a?
Yeah. That's a way of putting it. Let me hold on. Terminal velocity. Okay, terminal velocity is the highest velocity attainable by an object as it falls through a fluid. Air is the most common example. It occurs when the sum of the drag force and buoyancy, if it was water, is equal to the downward force of gravity acting on the object. Okay?
Got it.
So, terminal velocity. Now, that is not an enabling objective to know, but it is a great example if you were going to talk about equilibrium. If your instructor's like, okay, tell me about equilibrium. That is a great example. All right.
Got it.
Okay. Newton's second law is called the law of acceleration. And I'm gonna have to repeat that because I paused for a second for recording. All right, so atmosphere, properties of the atmosphere. The atmosphere is composed approximately 78% nitrogen, 21% oxygen, and 1% trace gases, okay, which is carbon dioxide, argon, neon, and helium. Actually, you could just say 1% trace gases, and for most instructors, that's fine. If you're talking about, but 78% nitrogen and 21% oxygen is definitely what you need to know. Okay, so the air that we breathe is actually a uniform mixture of gases. All right, so keeping that in mind, okay, we need to talk about pressure. All right, in your mind, what is pressure?
Pressure, when I think of pressure, I think of atmosphere, like the forces of the atmosphere, or pressure underwater. Like if you're in a deep swimming pool and you swim to the bottom 20 feet,
okay,
you feel a lot more pressure there than you do at the surface. That's an example of it. So those two examples are both pressure, downward acting pressures. Can't think of another one. Like, I can't think of a horizontal or vertical acting pressure. But that's when I think of pressure. Those are two examples I think of.
Okay. Good. All right. Let me do this. All right, static pressure. Static pressure is just the atmospheric pressure that's going on.
Sorry, 1 second.
Okay. All right, static pressure. Static pressure is the pressure particles of the air exert on, adjacent bodies. Okay. So right now, and in a standard atmosphere, it should be about 14.7 pounds per square inch, a column of air. If we trapped a column of air, the air molecules in that cube would be about 14.7 pounds per square inch at sea level. All right. Some other things that we could use. We could have a column of mercury. A column of mercury, when gravity acts on a column of mercury, it's actually, if we had it in a tube and open it up to the air, it would actually push up the mercury 29.92 inches. All right. And most barometers, your aircraft instruments are kind of calibrated to that as far as your vertical speed indicator and your altimeter. All right. So static pressure is just kind of like a reference. All right. It's normally perpendicular. The force of static pressure always acts perpendicular to any surface that the air particles collide with. All right. Whether the air is moving or not with respect to that surface. All right. The next thing, and what you will see is for static pressure, you will see a symbol like this. It'll be a big P and a small s, meaning that is static pressure. All right. Density, air density. Air density is the total mass of air particles per unit of volume. All right. Now, air density. Do you think it increases or decreases with altitude?
Air density, oxygen content decreases. I know that.
Okay.
Let's see.
At altitude, it'll probably be less dense, right?
Right.
Okay. That's why when people climb like really high mountains, normally they probably have, if the mountain pass goes above 10,000 feet, then they'll probably have some supplemental oxygen just to be able to keep their wits about themselves, because the air density is not as good as it would be at sea level. When I give people examples of this, I like to think of a pool. Do you swim?
Yes.
Okay. Have you ever been scuba diving?
I've not.
Okay. Have you ever swim? Do you ever swim to the bottom of a pool?
Of course.
Okay. Did it feel heavier or lighter?
Definitely feels heavier. You definitely feel it in your brain, like
Because
you feel the pressure all throughout.
the water molecules are all above you, and they are exerting themselves on you.
Right.
That's why it feels heavier. Well, we could think about the surface of the Earth the same way. When we're down here at sea level, the air density is high. But when we get in a plane and we go high, we don't have as much air. The air density is less. So we don't, it's not like we're down here in the bottom. Okay, where we have all that volume exerting itself on us. So down here we may have 14.7 psi, but at 39,000 feet, it might just be 7 psi.
So now, what forces cause your ears to pop when you're going up like a large mountain, driving or flying?
That's a difference in pressure.
That's totally unrelated.
What you feel is you have a tube called the eustachian tube that runs along here, and this is why we can blow and clear our ears and stuff like that. This is why it's not wise to fly with an upper respiratory infection. You can get sinus block. You could, oh my God, and you won't really feel it on the climb out. You'd be fine. You'd be great, because the air density is lessening, and so that internal volume is kind of like expanding, right? The pain comes is when that cavity tries to contract, and this is what's going to happen on the descent, and that's why, commercial pilots, they try to make their descents as shallow as they can do it. You know what I'm saying? And the flight attendants are actually trained to kind of look at people, see if they're experiencing any discomfort and stuff like that. So, because the pilot may have to be like, okay, look, we got to go to higher altitude for a little bit and help this person equalize a little bit better. So that's why.
I'm surprised I've never seen that when I've been flying, because I used to fly a lot on commercial, like just traveling, and I'm surprised I never saw that happen with a passenger.
Yeah, well, they probably were at a descent rate that was comfortable enough for them not to be too bad. And plus, another thing too is when, let's say I'm flying at 35, and I'm just generalizing, but let's say I am flying at 29,000 feet. This is the actual aircraft altitude. But inside the cabin, and in the cabin is basically a pressure chamber, I would probably have about 8,000. I would have it set for 8,000 feet. Okay. The pressurization system is going to set the environment for 8,000 feet. Okay. This is why on, like the movies and stuff, they're all dramatic. Because this pressure is equalizing with the outside pressure. What do we have? Low pressure or higher pressure outside?
Higher.
No, lower.
Yeah.
Because we're at 29,000 feet. So this is the environment outside of this pressure chamber. So if we have high pressure, we have low, and we have high inside here. And if we bust the window or something like that, everything's gonna suck out. So that's why they kind of over dramatize that. Another thing. Go ahead, I'm listening.
The papers and like the cups on the chairs, that you'd expect to fly out, but like would you actually be holding on to things like flying out, or no?
I think I would say no. You know why?
Why?
You ever see like movie? Well, it's another movie. I know, like when airborne rangers and stuff like that. Now they depressurize the whole system, but
are they jumping? They're not jumping at 29,000 feet, are they? Or
yeah, you could do a halo jump where you have to jump with oxygen.
wow.
They call it high altitude. They call it halo, high altitude, low open.
Okay.
So you could actually that could be a situation. But when they open that rear door of that C-141 or C-130 that you're jumping out, you don't see stuff getting sucked out, do you?
No.
You see wind and stuff like that. But
they're not holding onto their seats like for their life. No.
Right. Okay. So yeah. All right. So air density. All right. I'm gonna stay 1 point here. So is this pretty much is the information, is it pretty much absorbable? That's mainly what I try to make it as simple as I can.
Scalar and vectors in the beginning, that went a little fast. Maybe that's just because I hadn't heard or hadn't studied this stuff in a while since I passed the astb. But the definitions, they make sense. Like you said, it'll just take studying for these. Like, I don't know, if I were to get to API and I didn't have any background or I didn't study prior to getting to API, I'd definitely make flashcards on this stuff. Will you have to memorize these formulas down there?
Yes, I would memorize them. They're not that hard. You put them on flashcards. You know what I'm saying? Work equals force times displacement, acceleration, V sub 1 minus V sub 0 over time. Yeah. And what we will actually be doing is I'll have like little exercises where we will actually work these problems out. So when you get down there, you're just gonna run through that shit. You're gonna be like, oh, I'm done. And so this is so you look like the star. I wouldn't even tell them I've even been through an API prep course. I'd just be like, hey, I'm like, hey, you're a really good instructor. That's what I would do. I'd be like, because you're just a really good instructor, and I like the way you present the material. You know what I mean?
I
Instructors.
was thinking like a physics class at a local community college or something like that too, because I didn't take physics in high school.
Okay.
And as a business major, I don't touch that.
Yeah, you wouldn't need that. Yeah, you wouldn't be dealing with physics. I had to take 1 and 2. Oh man, let me tell you something. I understand it now, because I teach it. But I'm telling you, when I was in college, man, dude, I would actually literally leave physics 1 with like a headache. We had this real spaced out instructor. Like he was like out there, like his mind was like on a whole nother level, and he really could not come down to our level. And that's sad. That's really sad, because my thing is, if the student hasn't learned and the teacher hasn't taught, and you have a lot of instructors, they know their stuff, they know their material, but can they spoon feed it to someone? So and then to bring them up to that level,
you need to know your audience.
Yeah.
As an instructor.
And
you think it'd be helpful for me to take a physics class prior to all this, or?
No, I will give you everything you need. I'll give you everything you need. You don't need to worry about that. Okay. The next thing we need to talk about is temperature. Temperature it's a measure of the random kinetic energy of air particles. Okay. I don't like that. I don't like that definition. When I think about temperature, I think it is the degree of hotness or coldness of something. That's my temperature that I like, or not temperature that I like, but the definition that I like to use. All right. So the temperature. All right. Now, one thing that we have to understand is something called standard lapse rate in the atmosphere. What standard lapse rate is? Let's say you and I, we're in a space shuttle. All right. And we're going to take off. Don't laugh at my artwork, Jake. All right. So, as we take off and we launch, every 1,000 feet, something is going to happen. All right. So 1,000 feet, 2,000 feet, 3,000 feet, and we're climbing and so on and so forth. On the Celsius scale and the Fahrenheit scale, something is going to happen. On the Celsius scale, we're going to lose 2 degrees per 1,000 feet, and on the Fahrenheit scale, we're going to lose 3.5 degrees per 1,000 feet. This is called the standard lapse rate. So normally what the atmosphere should be doing as we climb up, when we pass through 1,000. So let's say, all right, for instance, it's, I don't know, 30 degrees. No, that's too. Let's say 50 degrees Celsius. At 1,000 feet, we should drop to 48. At 2,000 feet, 46, 44, 42. You get what I'm saying there?
Yeah.
Okay, so that is the standard lapse rate, or what we call a average lapse rate. All right. So what happens is, this is what happens in the troposphere. And trope in Greek means to change. So the temperature changes, all right, steadily. There should be a constant drop, 2 degrees. So it gets colder as we go up. Now
what happens? Colder, that means that the air molecules are more dense.
Right.
Right?
Mm-hmm. Mm-hmm. But they are more dense, and a lot of people will say, oh, well, the pressure should be, no, that's not true, because the atmospheric pressure, like the pool example I gave you. All right. So now what happens is, roughly about, let's say 39,000 feet. And it changes over the polar and equatorial regions. It kind of changes because of the compression and density and things of that nature. But this happens all to about 39,000 feet. All right. So that is a standard lapse rate or an average lapse rate. We lose 2 degrees per 1,000 feet in Celsius and 3.5 degrees Fahrenheit Celsius. All right. So icing is a major issue in the wintertime with aircraft. And if we are already at 32 degrees Celsius on the surface and there's snow and rain and stuff like that, it's only going to get worse. So we need to have de-icing and anti-icing equipment. All right. And we have those on airplanes, like on special instruments like our pitot tubes and static ports. We have elements, electric elements that we can put in them to keep them warm enough so that they don't freeze over. Okay. So you would actually take off with these mechanisms on so that your flight instruments read properly.
Like the little things in your car, the rear window.
Yeah, very similar to that. Yeah, very similar to that. But it's kind of like these instruments are already metal, so they run an element through them, an electrical element. You flip a switch, and it just keeps it warm enough. So if something did want to attach to it and freeze on it, it wouldn't let it. It'd be too warm. It'd be above 32 degrees Fahrenheit or 0 degrees Celsius, which is freezing for water. All right. Now, after that, what happens from 39,000 feet to about 66,000 feet? We have a constant layer of temperature. So what we call this is a tropopause. This whole area is the troposphere. And the temperature changes at the tropopause. All right. So trop, which means the change in Greek, the change stops. And then we go through an isothermal layer from around roughly 36 to 39 to 66,000 feet. All right. Okay. This is all boring stuff, dude, but you will see this at API.
No, I know it's going to be there.
Guaranteed. Now, the speed of sound. We talk about something, or we discuss something called the local speed of sound. And it is the rate at which sound waves travel. Okay. The speed of sound increases so let me word this properly. If the speed of sound was 600 miles an hour at sea level, when we increase altitude, it's going to be slower. It's going to probably be like 500, 475. I'm just throwing numbers out there, but just to show you that the speed of sound will slow down, because I think it's because of the decrease in density. The speed of sound in the air is dependent upon temperature of the air. All right. The warmer the air, the more excited the particles are. All right. So if the particles are more excited where it's warmer down at sea level, when it gets colder, okay, the temperature drops and the local speed of sound decreases. So, like I said, a good rule of thumb, as the temperature of air increases, the speed of sound increases. That's a good memory aid. Now, we talked about a standard atmosphere. This is what we calibrate our instruments to. When they put in an altimeter, all right, and these are standard in a perfect atmosphere. I talked about 29.92 inches in Hg. That is the chemical symbol for mercury. Standard temperature at sea level is 59 degrees Fahrenheit. All right, or 15 degrees Celsius. Is it 59 degrees right now? Where you are?
A little warmer in Connecticut than that.
Okay, so but these are just basic values. Okay, it's not like, okay, it's definitely going to be this. All right, and the local speed of sound is normally Mach 1, which is 661.7 knots. All right. So Mach 1 at sea level and Mach 1 at 39,000 feet are going to be different numbers. It's going to be slower. Okay. You're going to need to know different types of altitudes. And where are we at? How long we been on here, Jake?
We started at E20, I want to say.
Okay. All right. Okay.
Your first message was at 8:17.
Okay.
Yeah.
All right. We'll cover the altitudes because I want to keep this like around like an hour. This is a lot of material to absorb.
It is.
You know, and I don't want you to plateau. But there will be, this video will be posted, and so you can come back and you can look at it and stuff. But this is kind of like just a marketing tool, pretty much for people that have already taken the astb-e and they got a slot and they're going to be coming to API.
Your board and everything will be the main feature on the video too, right?
Yes.
Yeah, you want that on there because like that helps for visual learners especially.
So yeah, it's up there. Okay, so let's talk about altitude. All right. There is a memory aid, and I think it's ICE-TG. ICE TG. Yeah, that's it. And this concerns airspeeds. All right. The I stands for indicated. And let me type this in while. All right. Of altitude. All right, memory aid from remember types of altitude. ICE-TG. Okay, the I stands for indicated. All right. Indicated airspeed is the airspeed directly read off of the altimeter, the airspeed indicator. Okay. We also have calibrated airspeed. Let me type this in.
Which airspeed accounts for oncoming wind?
I'll talk about that in a minute. All right.
Okay.
Calibrated airspeed is indicated airspeed, what you see corrected for instrument and installation error, or the way it's positioned. All right. So the I is indicated, the C is calibrated, and calibrated indicated is what you see directly on the instrument. Calibrated is indicated airspeed corrected for instrument like position error and installation error, because there may be plumbing involved, but depending on how big your aircraft is, you know, the plumbing and stuff like that. The echo equivalent airspeed. All right, it is the speed at sea level under what we call standard atmospheric conditions, that 59 degrees Fahrenheit, 15 degrees Celsius, 29.92. All right. It's your speed at sea level under standard conditions. That's basically what it is in a nutshell. And I will go in depth. True airspeed. Your true airspeed is it's the speed of an aircraft relative to the air mass in which it's flying. All right. And when we talk about true airspeed, we're going to take temperature into account. It kind of, you know, it messes with the numbers a little bit to get it from true, from indicated to true. And sometimes what you will have in the airspeed indicator is a temperature scale to kind of adjust it to know what your true airspeed is. And then finally, G is our ground speed, which is our speed that we're actually moving over the ground. A good example of ground speed is, let's say our aircraft is flying this way, and we have a 20-knot wind, and our speed we're moving is 100 knots. So we're getting a tailwind. We're going to be moving 120 knots over the ground. Conversely, if we fly in this direction at 100 miles an hour and we have a 20-knot headwind, how fast are we going to be moving over the ground?
We're moving at 120 knots and we have 100 knots at our back.
Yeah, in this situation. So the winds are blowing this way in both cases. So we're going that direction.
Oh, so then we'd only be moving 80 knots.
Very good. We'd be 80 knots in this direction. Okay. So, that's what I'm going to freeze it there for the first hour, man. I really